Welcome back to the Deep Dive. Today we're really focusing in on something you've been asking about, voice AI, specifically voice agents and where they stand right now in 2025.
Right.
The idea is to give you a quick but really thorough understanding of this whole area.
And basically, what these voice AI agents do at their core is listen, respond in a useful way, and then, keep that going. Repeat.
Yeah, keeping the conversation flowing.
Exactly. It's all about making it feel natural, like a real conversation.
Okay, so let's maybe break down the typical setup. What's the architecture usually look like?
So for a production agent, usually in the cloud, it starts with capturing the speech, right? Your microphone digitizes it, sends it off to the cloud. Then it gets transcribed audio to text.
Oh, okay.
That text goes into the LLM, the big language model, the AI brain, if you will. It looks at the prompt, the context from the chat so far.
Right, the history.
Yeah. And then the LLM spits out a text reply. That gets turned back into speech using text-to-speech, TTS.
And then that audio comes back to the user.
That's the loop. And it's really important to get why it's mostly cloud-based right now.
The processing power needed.
Exactly. These AI models are computationally hungry. Plus, a lot of use cases are still, phone calls. Your average phone doesn't have the horsepower to run these models locally.
Makes sense. So for this deep dive, we're going to hit the big questions people have. Things like which LLMs are actually best for voice?
Right. And how do they keep track of the conversation, the context management?
Yeah, and how they connect to the real systems, back-end stuff.
I'm calling, yeah.
And critically, how do we even know if they're any good? Performance evaluation, evils.
Ready to jump in.
Let's do it. And I think the first place to start, the thing that really changes the game for voice AI is latency.
Right, latency. You hear that term a lot. Sounds like it's the big difference compared to just typing back and forth with an AI.
That's absolutely spot on. I mean, think about it. In a text chat, a small delay. Maybe annoying, but okay.
But in a real conversation, we humans, we expect a response almost instantly. We're talking like half a second, 500 milliseconds, give or take.
Anything longer just feels wrong, awkward.
Yeah, it breaks the flow, feels unnatural, yeah.
So when we talk about latency for voice AI, what exactly are we measuring? It's not just the AI thinking time, is it?
No, not at all. And that's a crucial point. You'll see providers quote latency numbers, but often that's just their server-side inference time. That's part of it, but it's not the full voice-to-voice latency the user actually feels. You've got to add up every single step.
Okay, like what?
Well, the audio capture on the device itself, encoding that audio, the network trip to the cloud, the trip back,
Right.
then the server processing, unpacking the data, maybe jitter buffers, smoothing things out.
Jitter buffers.
Yeah, they handle variations in packet arrival times over the network. Then the actual transcription time, the LLM thinking time, the time to first token. Then the text-to-speech generation, and finally sending that audio back and playing it. It all adds up. Every millisecond counts.
Wow, okay. And measuring that whole chain accurately sounds tricky.
It really can be. Some delays happen deep in the OS, and many tools just measure time to first byte of audio coming back, which is useful, don't get me wrong.
But not the whole story.
Exactly. It doesn't capture things like how long it took the system to even decide the user finished speaking, or variations in network round trips.
But I heard there's a kind of low-tech way to get a decent measurement.
Yeah, there is. Honestly, the simplest way is just record yourself talking to the agent.
Okay.
Load that recording into any audio editor, Audacity, whatever, and just visually measure the gap from the end of your voice waveform to the very start of the agent's response waveform. It's manual, yeah, but it gives you a real-world number.
That actually sounds pretty effective.
It is. If you're serious about production voice AI, you should probably do this regularly. Maybe even try simulating bad network conditions, packet loss, that kind of thing. See how it holds up.
So what's a good target then? What should teams be aiming for, that voice-to-voice latency?
For conversational stuff, aiming for around 800 milliseconds is a pretty solid goal right now.
Okay.
If you look at a typical, say, 1 second round trip, you've got maybe bits for the mic, encoding, network each way, transcription, the LLM's first chunk of output, the TTS, it all takes a slice.
Right.
Getting consistently under 800 meters with today's big models, it's challenging, but doable with good optimization. People have hit 500 meters.
Wow.
Yeah, but that usually involves Co-locating everything in one super fast compute cluster, maybe sacrificing some output quality for speed. It's not the common setup yet, mainly due to cost and, well, everyone still wants the best, most capable models, which are often proprietary.
Right, the trade-offs. Okay, latency is clearly huge. And understanding that naturally leads us to the models themselves, the LLMs. Their speed is a big part of that latency equation.
Exactly.
So which LLMs are really shining for voice applications right now?
Well, you could say the modern era really kicked off with GPT-4 back in March 2023. That was kind of the first one that could properly handle flexible, multi-turn chat and follow instructions well enough for useful tasks.
And now?
Now, its successor, GPT-4o, is, well, pretty dominant in the conversational voice space. I think a key thing with GPT-4o is its architecture. It handles different data types better, which helps speed things up for voice.
Yeah.
That multimodal capability gives it an edge.
But it's not the only game in town anymore, is it?
Oh, definitely not. We're seeing other models now that are matching or sometimes even beating the original GPT-4 on the things that really matter for voice.
Like what specifically?
Okay, so low latency, obviously. Good instruction following is critical. Reliable function, connecting to other systems.
Yeah.
Low rates of hallucination or just making stuff up.
Right.
And even things like personality and tone, getting that right. And of course, cost is always a factor. GPT-4o also improved on many of these compared to the original GPT-4, by the way.
So for demanding stuff, you generally still want the best available model.
Yeah, that usually makes sense. If the use case is complex, you probably want the top-tier model.
What about the newer players entering the scene?
Definitely keeping a close eye on Google's Gemini 2.0 Flash. That landed February 2025. It looks like a major contender for voice.
What's that?
It's fast. It seems to rival GPT-4o on instruction following and function calls. And crucially, the pricing is really aggressive.
The cost factor again.
Yeah, this could be a big deal. That cost reduction might open up whole new categories of high-volume voice apps, maybe moving it from just premium use cases to being like a standard way to interact.
Interesting. So speaking of speed, how do they stack up on that time to first token, the TTFT?
Right, that's key for responsiveness. So for GPT-4o, the median TTFT is around 510 milliseconds. The P95, the 95th percentile, is higher, maybe 1360 minutes.
Okay.
And others. Claude Sonnet 3.5 is a great model, but latency hasn't seemed like its top priority. Its median is more like 840 meters, P95 around 1960 meters. Now, Gemini 2.0 Flash, this is where it gets interesting. Median around 460 meters, P95 about 1610 meters.
So faster median than GPT-4o currently.
Yeah. The rule of thumb we're kind of seeing is TTFT under 500 meters. That's generally good for a fluid conversation.
And interestingly, you mentioned GPT-4 Mini isn't faster.
Yeah, counterintuitively, the mini version doesn't actually give you a TTFT advantage over the full GPT-4 right now. TTFT is just so critical because it's how fast the agent starts talking back, that perceived responsiveness.
Okay, and let's circle back to cost. How big a difference does that Gemini Flash pricing make?
It's a potentially huge. Inference costs have been dropping fast, so it wasn't always the main thing. But Gemini Flash looks like it could be, I don't know, maybe 10 times cheaper than GPT-4o.
Wow, 10 times.
Yeah, potentially. That could completely change the economics, especially for longer calls. Like a 3-minute call might be, say, just under a cent with GPT-4o, maybe 1.2 cents with Claude Sonnet. But with Gemini Flash, it could be like 0.04 cents. Tiny.
And that scales up.
Massively. A 30-minute call could be 75 cents for GPT-4o, 90 cents for Claude, but maybe only 3 cents with Gemini Flash.
That's a massive difference.
It is, but you have to remember costs often go up faster than linearly with session length because the context window grows, right? You're sending more history each time. So techniques like caching the context, maybe summarizing older parts of the chat, become super important for long calls. OpenAI's real-time API does some automatic token caching, which is really helpful there.
Okay, that cost difference is definitely something to watch. What about open source models, Llama and others? How do they fit in for voice?
Yeah, so models like Meta's Llama 3.3 and now 4.0, they're showing really impressive benchmark scores, sometimes beating original GPT-4.
But for voice AI production use?
Generally, for most commercial apps today, they're probably not seen as better than, say, GPT-4o or Gemini, unless you have a really specific need to run the model locally on your own hardware.
Right. And Meta doesn't offer a hosted Llama API directly, do they?
No, but plenty of other cloud providers do host it. We do expect a lot of movement in open source this year, 2025. You've got potential new models from Alibaba with Qwen, DeepSeek, Google's Gemma, Microsoft's Phi.
So the gap might close.
It could. We might see some really competitive open weight options emerge specifically good for voice, and fine-tuning these, like Llama 3.37 B, can already be a good starting point for very niche tasks.
Okay. So far, mostly text in, text out. But the really cutting-edge stuff seems to be speech in, speech out directly, these speech-to-speech models.
Yes, that's a super exciting area and pretty new. Imagine just talking to the LLM and it talks right back in audio. No separate transcription, no separate TTS.
The potential benefits seem huge. Lower latency, more natural understanding.
Exactly. Better understanding of tone, nuance, maybe even background sounds, and potentially much more natural human-like voice output. Both OpenAI and Google have APIs for this now. The feeling is this is likely the future direction.
But, sounds like there's a but, not quite ready for prime time everywhere yet.
That's a fair to say, yeah. While the voice quality from the best ones, like OpenAI's GPT-4o audio preview, is often undeniably more human than standard TTS, there are still hurdles. Latency should be lower in theory, but audio is just data richer than text, more tokens.
Right.
So ironically, for long conversations, these models can actually be slower right now because of that bigger context.
Huh.
We also see some slightly odd output glitches sometimes in audio mode, like repeated words, unfinished sentences, things less common in text output.
So how do people handle the context size issue?
One approach is a hybrid. Use audio for the latest user turn, but use text for the older conversation history. That helps keep the token count down.
Makes sense.
OpenAI's real-time API, which uses a smaller audio model, has great voice quality and speed, but maybe isn't quite as good at following complex instructions or managing long context as the full GPT-4o.
And Google's.
Their multimodal live API looks very promising, long context, strong audio understanding, but it's still pretty early days. We'll definitely see big progress in speech-to-speech in 2025. Will it be the default for most production apps this year? Still an open question, I think.
The key challenge seems to be balancing that naturalness with the current latency and reliability issues compared to the established text-based ways.
Precisely. Research is likely focusing hard on making audio tokenization more efficient and handling that long audio context better.
Okay, so if speech-to-speech isn't the universal answer yet, that brings us back to the first step in many pipelines. Getting the user's voice into text, speech-to-text, transcription. What matters most here?
For voice AI, it boils down to two things mainly. Super low latency and super high accuracy, low word error rate, basically.
Usually you have to trade those off against each other.
Often, yeah. Optimize for pure speed. Accuracy might dip a bit. There are great transcription models out there, like open source Whisper. But Whisper is typically too slow for real-time chat. TTFT is often 500 meters or more. Just not snappy enough.
So is there a clear leader for production use right now?
Overwhelmingly, yes. Most production voice AI agents today are using DeepGram.
DeepGram, okay. Why them?
They've just really focused on hitting that sweet spot. Low latency, they quote around 150 meters TTFT in the US, combined with very good accuracy and decent pricing. They offer APIs, but also Docker containers you can self-host.
Self-hosting DeepGram, why would you do that instead of the API?
Few reasons. Data privacy is a big one. Some companies just want total control, especially with sensitive data or strict regulations.
Right, like healthcare or finance.
Exactly. Also, latency outside the US, their main servers are US-based. So using the API from, say, Europe might add latency maybe 250 meters TTFT. India, maybe 350 meters. Self-hosting closer to your users can cut that down. And they offer fine-tuning services, too. If you have really specific jargon, accents, weird vocabulary, fine-tuning can boost accuracy for your specific use case.
That makes sense. But what if the transcription isn't perfect? Even with the best models, errors happen? Any way to deal with that?
Yeah, and this is actually pretty clever. Because today's LLMs are so good, you can kind of prompt them to expect errors.
How does that work?
Well, the LLM gets the transcript, but it also has the whole conversation history. So you can literally tell it in the system prompt, hey, this input is a transcription of speech. It might have errors. Use the context to figure out the real meaning.
You give it examples?
Yeah, like correct likely errors. For example, if you see buy milk 2 tomorrow, interpret that as buy milk tomorrow. It's surprisingly effective at helping the LLM recover the user's actual intent.
That is clever. Are there other interesting things happening in STT we should know about?
Oh yeah, it's a busy space. OpenAI just released their own STT models, GPT-4o Transcribe, and a mini version. Gladia, popular for French, is expanding languages. Speechmatics, Assembly AI older players, are now focusing more on conversational speed, getting faster TTFTs. NVIDIA is releasing competitive open source models.
What about Grok? They're known for speed.
Right. Their hosted Whisper Large V3 Turbo is hitting under 300 meters TTFT now. That's the first Whisper API we've seen fast enough to really be in the running for real-time conversations.
And the big cloud providers, Azure, Amazon, Google.
For low latency English, they're generally not quite matching DeepGram yet, but if you already have a big deal with them or you need strong non-English language support, they might still be the right choice. Language support varies a lot.
And you mentioned using Google Gemini itself for transcription. That sounds different.
Yeah, it's a really interesting kind of new approach. It uses Gemini 2.0 Flash's built-in audio understanding, and it's low cost.
So how does it work?
You run 2 Gemini inferences in parallel for each user turn. One takes the audio in and figures out the conversational response, audio and text out. The other takes the same audio in and just transcribes it, audio in, text out.
Okay, then what?
Then, for the next turn, instead of sending the full audio history back to Gemini, you swap out the last user turn's audio with its text transcription from that parallel process.
So you use Gemini's audio smarts for the current turn, but save tokens on the history by using text.
Exactly. Gemini's per token cost is so low, this can actually end up being cheaper than using a separate STT service like DeepGram. It's using Gemini's audio understanding, mind you, not as a full speech-to-speech model here.
What are the downsides?
Well, it's still experimental. The transcription latency probably isn't quite as low as dedicated STT. It adds complexity managing those parallel calls and context swapping. And maybe a general LLM is slightly more prone to prompt injection or context errors than a pure transcription model, but potentially better understanding and transcription quality. It's a trade-off.
Wow, this space is moving fast. Okay, so we've got speech into text. Now let's flip to the other side. Text to speech, getting the agent's response back out as audio. What makes a good TTS system?
Several key things. Naturalness is probably number one. How human does it sound? Pronunciation, rhythm, intonation, prosody. Then latency again, but here it's often called time to first byte, TTFB. How quickly does that audio start streaming back?
Right, keeps the conversation moving.
Exactly. Cost, obviously. Language support, how many languages and voices, increasingly important. Word-level timestamps?
Word-level timestamps. Why?
We'll get into that more with interruptions, but basically knowing exactly which word was being spoken at any given moment is crucial for managing context accurately if the user jumps in.
Got it. And customization?
Yeah, ability to tweak voices, pronunciations, accents, that can be important too.
It feels like TTS has gotten way better recently.
Oh, massively. 2024 saw a big jump. Lots of new startups, big improvements in quality and latency from the leaders.
And who are the leaders? Is it the big cloud guys again?
Interestingly, no, not really for the best real-time conversational voice. Most developers building cutting-edge voice AI are actually using TTS from specialized startups right now. Their models just tend to sound better and react faster for the specific use case compared to, say, Azure's or Google's standard TTS offerings.
Startups are standing out.
Okay. Alphabetically, you've got labs like Cartesia. They use a different model architecture, state space models, getting high quality with low latency.
Yeah.
DeepGram, yep, them again. They have a TTS offering focused on low latency and cost.
Wow.
11 Labs, probably the best known for sheer realism, emotional range, really nailing that human-like quality. And Rhyme, they focus on customizable voices specifically trained on conversational data.
And they all have APIs. Can you self-host?
All have good APIs. Cartesia, DeepGram, and Rhyme also offer self-hosting options, which is great for privacy or latency control, similar to the STT side.
How do they compare on cost and speed?
There are trade-offs, as always. Looking at data from early 2025, DeepGram is super fast on median TTFB, maybe 90 meters and cheaper per minute, but its P95 latency is higher.
Really?
Cartesia and Rhyme offer a really nice balance of quality and speed. Median TTFB, maybe 170 meters for Cartesia, 310 meters for Rhyme. 11 Labs really pushes for realism, but that comes with higher latency, maybe 700 meters median TTFB.
And non-English languages?
That varies a lot between providers. If you need languages other than English, you really have to test thoroughly. Quality and voice availability can be quite different.
What about mispronunciations, proper names, jargon?
Super common problem. Most good services offer ways to steer pronunciation, maybe phonetic spellings via the API or custom lexicons.
And if your service doesn't have that?
You can often get the LLM to help. Instruct it to output sounds like spellings in the text it sends to the TTS. Instead of NVIDIA, have it send NVIDIA, or GPU becomes GPU.
Huh. That's a neat trick. Okay, back to those word level timestamps you mentioned. Why so critical again?
Right. Imagine the user interrupts the agent mid-sentence. To keep the conversation context accurate for the next LLM turn, you need to know exactly what text corresponds to the audio the user actually heard before they cut in.
Ah, I see. So you don't feed the LLM text the user never heard.
Precisely. Good TTS services provide timestamps alongside the audio stream, telling you when each word starts and ends. This lets you reconstruct the heard text accurately. Cartesia's API is a good example of providing this data.
And good streaming support helps with this.
Definitely. A solid real-time streaming API from the TTS provider makes handling interruptions and even parallel audio generation much smoother. Cartesia and Rhyme have quite mature streaming support, especially within frameworks like PipeCat. We expect more progress here in Audio 25 rumors of new models. OpenAI has a steerable mini TTS coming. Roke is partnering with PlayAI for low-latency multilingual stuff. It's moving fast.
Okay, STT gets audio in, TTS gets audio out. But there's a lot happening to the audio itself in the middle, right? The audio processing pipeline.
Absolutely. And while a good platform often hides this complexity, if you're building complex agents, you'll eventually run into issues where understanding this pipeline is key to fixing things.
So give us the quick tour.
Okay, quick tour. It starts, obviously, with the microphone. Modern mics are smart, often have automatic gain control, AGC, built in.
Adjusting volume automatically.
Right, compensating for how far you are, etc. But things like Bluetooth mics, they can add hundreds of milliseconds of latency sometimes, and it's often out of your control as a developer. AGC itself is usually on and often hard to fully disable on consumer gear.
What about feedback, speaker to mic?
Echo cancellation. Vital for speakerphones or laptops without headphones. It prevents that horrible loop. It's very latency sensitive, so it has to run locally on the user's device.
Built into browsers and stuff.
Yeah, good news is it's usually built into telephony stacks, WebRTC, and browsers. Chrome, Safari are generally good. Firefox, maybe not quite as robust. But if you roll your own pipeline, like with WebSockets and React Native, you have to implement echo cancellation yourself.
Okay, noise. Speech versus music.
Right. Telephony and WebRTC usually default to speech mode, narrower frequency range, optimized for compression, noise reduction. Older phone systems might even be stuck at crappy 8 kilohertz quality.
But WebRTC can do better.
Oh, yeah. Default is usually 48 kilohertz mono, using the Opus codec at maybe 32 kilohertz species. Great for speech. But if you need to handle music, those settings aren't ideal. You'd want to disable echo noise suppression, maybe enable stereo, crank up the Opus bitrate.
Opus codec, you mentioned that, and encoding in general.
Encoding is just formatting the audio for the network. Common ones for real-time are raw 16-bit PCM, very high quality but huge bitrate, bad for internet. G.711 old phone standard, and Opus the Star for voice AI.
Why Opus?
Low latency, super efficient, works well across a huge range of bitrates, handles speech and music well. It's the default in WebRTC for good reason.
What about noise reduction on the server side?
Interestingly, modern STT and VAD models are pretty good at ignoring general background hiss and hum, so traditional noise suppression is maybe less critical than it used to be for pure AI interaction.
But what about other voices in the background? Like in an airport?
Good point. That's where primary speaker isolation comes in, suppressing other people's speech. That's still really valuable for transcription accuracy in noisy places. Crisp is kind of the leader here, but it's more enterprise. OpenAI's real-time API also just added some noise reduction.
Okay, and one last piece. Voice activity detection. VAD.
Yep. Fundamental part of almost every pipeline. Basically classifying audio chunks. Is this speech or not speech? It's crucial for figuring out when someone stops talking, which we'll dig into right now when we talk about turn detection.
Excellent. So processed audio needs to travel. Network transport. What are the choices for voice AI?
Okay, for streaming audio in real time, the two main contenders are WebSockets and WebRTC.
And the winner is?
For production client-server voice AI, especially in browsers or mobile apps where low latency is paramount, strongly recommend WebRTC.
Why not WebSockets? They're common.
WebSockets are fine for server-to-server stuff or maybe early prototyping where latency isn't make or break. But for real-time media, they have issues. Such as?
Okay, big one. WebSockets run over TCP. TCP suffers from head-of-line blocking. One delayed packet holds up everything behind it. Bad for real-time.
And WebRTC?
Often uses UDP underneath. Plus, Its Opus codec is tightly integrated with WebRTC's own smart congestion control. It handles packet loss better, especially with Opus's forward error correction.
Okay. Other advantages for WebRTC.
Yeah, automatic timestamping of audio simplifies things a lot. Detailed performance stats built in great for monitoring. Reliable reconnection logic is harder with WebSockets. And good WebRTC implementations bundle echo cancellation, noise reduction, AGC.
So WebRTC for the real-time stream. What about plain old HTTP? Still used?
Oh, absolutely. Still fundamental for service interconnection. REST APIs, webhooks, all HTTP. LM inference itself, when it's text-based, usually happens over HTTP.
Yeah.
Base agents use HTTP constantly to talk to external services, internal APIs, often proxying those function calls we talked about via HTTP endpoints.
So an app might use both. Very common. Multimodal apps might use WebRTC for the voice stream and HTTP for fetching data or sending commands. You just need to manage state across both connection types carefully.
Downsides of HTTP for real-time media itself.
Yeah, higher connection setup latency, harder to do long-lived bidirectional streams. WebSockets are better there. Still vulnerable to TCP head-of-line blocking. And sometimes binary data gets base 64 encoded, which bumps up the bitrate.
You mentioned QUIC and MACH earlier. Quick refresher.
Right. QUIC is a newer UDP-based transport protocol, powers HTTP3. Faster connections, avoids head-of-line blocking, built for bidirectional streams. Google, Facebook are rolling it out. It's likely the future for a lot of media streaming.
But not quite there for voice AI yet.
Adoption takes time. Safari, for instance, doesn't fully support web transport yet, which is the QUIC version of WebSockets. Mock Media over QUIC is an IETF group working on a simple, low-latency standard specifically for media on QUIC. Real-time voice AI needs are actually influencing its development, so watch that space.
Okay, protocols matter, but surely the distance the data travels matters too. Physics.
Absolutely critical. Long network paths kill low-latency apps no matter the protocol. Servers need to be physically close to users.
How close?
Example, UK user talking to an AWS server in California. That round trip might add over 100 meters compared to talking to a server in Europe. That's a huge chunk of your 800 meters budget gone right there.
So how do you serve a global audience well? Build data centers everywhere.
Ideally, yes, but that's crazy expensive. Needs dozens of sites for truly global 15 meters latency. Plus, finding GPUs everywhere dealing with services that aren't global, it's hard.
So what's the practical solution?
Edge routing. The idea is connect the user to an edge server near them. Then use private optimized network backbones for the long-haul part to your main servers instead of the messy public internet.
Does that help much?
Big time. Using that UK to US West example again. Edge routing might not just lower the median round-trip time, but more importantly, it drastically cuts down jitter, the variation in packet arrival times.
And less jitter is good because
jitter buffers have to be bigger to handle more variation. And bigger buffers mean more perceived delay for the user. So less jitter, smaller buffers, better experience.
So use infrastructure providers that offer edge routing.
Exactly. And ones that give you good performance metrics so you can see what's happening.
Okay, we've got audio in, processed, transported, response coming back. But how does the system know when is the agent's turn to talk? Turn detection. Sounds simple, but you hinted it's tricky.
Oh, it's surprisingly complex. Academics call it phrase detection, speech segmentation, endpointing. The fact there's so much research tells you it's not trivial.
Yeah.
Even humans mess it up sometimes, right? We interrupt or pause awkwardly.
Yeah. So what's the standard way AI does it?
The most common way today is using pauses, detected by that voice activity detection VAD model we mentioned.
The thing that tells speech from silence.
Exactly. VAD is better than just looking at volume. It classifies short audio chunks speech or no speech. You can run VAD client-side, maybe for wake words, but usually it's easier server-side, especially for phone calls, where you can't run code on the user's end device.
Which VAD model is common?
Celero VAD is probably the most widely used open source one. It's efficient, works for multiple languages, handles different audio quality, even runs in browsers via WebAssembly.
How does it decide a pause means the turn is over? Is it just a timer?
Basically, yeah, but with tunable knobs. You configure things like how long does the silence need to be? How short a burst of speech counts as starting to talk? How confident does the VAD need to be? Minimum volume, maybe. Tuning these is key to getting good behavior.
Just relying on pauses seems like it could go wrong. People pause mid-thought.
Totally. Too long a pause threshold, the conversation drags. Too short, the agent jumps in too soon. Both are bad experiences.
So, alternatives.
Well, there's push to talk, User holds a button, unambiguous, but changes the whole feel. Not possible for phone calls, obviously.
Right.
It's less common. Endpoint markers. Explicitly saying over, or some command phrase. Works for very specific things, but feels unnatural for general chat.
Seems like the dream is the AI just knows from context like a human.
Hmm.
Any progress there?
Yes. That's context-aware turn detection. It's a big R&D area. Humans use filler words, grammar, patterns, like knowing a phone number is complete, intonation.
Uh-huh.
Deep learning models are great at patterns. LLMs know grammar. So people are building models to use that context.
Oh.
Two main ways emerging. One, a small, fast, specialized turn detection model. It works with a short VAD timeout, analyzes the audio, and only triggers the main LLM when it thinks a full phrase is done. Pipecast community actually has an open source one.
Okay. And the second way?
Use the big LLM itself. With clever prompting, maybe few-shot examples. But LLMs are slower, so this usually needs a parallel setup. One pipeline figures out the turn-in, another maybe starts greedily inferring on the audio chunks as they arrive so it doesn't block.
Sounds complex.
It is. OpenAI also just launched what they call semantic VAD in their real-time API. Uses context, unlike their older pause-based server VAD. So lots of movement here.
Okay. Natural conversation also involves interrupting. What happens when the user talks over the agent?
Handling interruptions gracefully is super important for making it feel natural. It means everything in your pipeline needs to be cancelable, fast, and you need to stop the agent's audio playback on the client, like instantly.
Do frameworks help with stopping the processing?
Usually, yeah. The framework often handles killing the pipeline tasks, but if you're using low-level audio APIs that send audio faster than real-time, you might need to manually code the part that stops playback and clears any buffered audio the user hasn't heard yet.
What causes bad interruptions? Like the agent interrupting itself or triggering on noise?
Several common culprits. Random noises, coughs, clicks can sometimes fool the VAD. Tuning VAD sensitivity helps, but it's a balance. Too insensitive, you miss short phrases. Echo cancellation failing, especially right when the agent starts talking after silence. That can cause self-interruption. Tweaking VAD, minimum start length, maybe smoothing audio volume can help there.
And background speech again.
Right. A basic VAD can't tell the user from someone else talking nearby. Speaker isolation processing is the best fix for that, if you can use it.
And if an interruption does happen, how do you keep the conversation context correct? You mentioned timestamps earlier.
Exactly. Because LLMs generate text fast, the agent might have generated, maybe even started playing, stuff the user cut off and never heard. The context you feed back to the LLM for the next turn must match only what the user actually heard.
So you use the TTS timestamps?
Yes. If you have word-level timestamps from your TTS, you can buffer the agent's text response and piece together only the part that corresponds to the audio played before the interruption. Good frameworks like Pipecast often handle this synchronization logic for you. It's critical for keeping the conversation coherent.
Okay, makes sense. We've talked a lot about the back and forth. How do these agents actually remember what's been said? Managing conversation context.
Right, fundamental stuff. LLMs themselves are stateless. They have no memory turn to turn.
So you have to remind them every time.
Pretty much. For every single turn, you have to send the entire conversation history back, all the user messages, all the agent messages, plus system instructions, configuration stuff.
The whole transcript gets sent back and forth.
Essentially, yes. Plus, the system prompt defining the agent's persona and goals, any tools or functions it can use, settings like temperature controlling creativity, all of it goes in each time.
Do all the LM providers handle this the same way? OpenAI, Google, Anthropic?
The basic idea is the same, but the specifics of the API formats differ. How messages are structured, how functions are defined, where system instructions go, it varies.
So people build wrappers.
Yeah, lots of third-party libraries or gateways try to translate, often mapping everything to OpenAI's format as a kind of standard. But they're not always perfect, might lag behind new features or have bugs. There's a debate about how much abstraction is good versus talking directly to each API. Pipecast, for example, does offer translation layers.
Managing this growing context sounds like work. But does it offer any advantages?
It does add complexity, yeah. But it also gives you flexibility. You're not just appending messages. You can actually modify the context between turns.
Like what?
Like summarizing older parts of a really long conversation. That can cut down latency, save costs, and sometimes even make the LLM perform better by keeping the context focused and within its optimal limits. We'll touch on this more when we talk about scripting.
Okay. A huge part of making agents useful is letting them do things. Interact with the world. Function calling. Sounds crucial for production.
Absolutely critical. Production agents rely heavily on function calling.
For what kinds of things?
All sorts. Retrieval, augmented generation, RG fetching info from databases or APIs, talking to existing back-end systems, integrating with telephony, doing call transfers, sending DTMF tones, even controlling the conversation flow itself, like moving between states in a predefined script.
How reliable is function calling in today's LLMs, especially for complex voice stuff?
That's a really important question. The best LLMs are getting better, definitely. But voice AI really pushes the boundaries. Why? Because you often have multi-turn conversations, the context gets long and complicated. You might define many different functions. You might call them repeatedly.
And that's harder for the models.
It can be. These patterns, long context, many functions, repeated calls might be a bit out of distribution compared to what the models were mostly trained on. So even if a model aces a standard function calling benchmark, it might still stumble in a real complex voice app. You absolutely need custom evaluations, custom evals, to test your agent's function calling in realistic scenarios.
Function calls sound powerful, but also like they could slow things down,
Yeah.
latency impact.
You're right, they definitely add latency. Several reasons. One, it's usually 2 LLM calls minimum. First, the LLM says, I need to call function X. Then you run function X. Then you call the LLM again with the result.
Okay, double inference.
Yep. 2, that initial request from the LM to call the function usually isn't streamed. You need the whole request before you can run it. 3, just having lots of function definitions in the prompt can sometimes slightly slow down the LLM's initial response time. And 4, the function itself might just be slow, talking to a legacy database or a third-party API.
So how do you manage that delay for the user? You can't just have dead air.
No way. You need quick on your feedback. If you know a function call might take a while, best practice is either always say something short first, like, okay, let me check that for you before you call the function, or have a timer. If the function doesn't return in, say, 3 seconds, play a little still working on it message. For really long things, maybe even some subtle background hold music.
What if the user interrupts during a function call? That sounds messy.
It can be. Good point. LLMs are trained to expect function calls and responses to come in pairs in the history. Request, then response.
So if it gets interrupted?
You still need to put a response in the context, even if that response is just canceled by user interruption. You can't leave a function request dangling unanswered. That confuses the LLM, makes it less likely to call functions reliably later.
Ah, okay. So the history needs that pair.
Yes. Frameworks like PipeCat help manage this. If a function is marked interruptible, and the user talks, PipeCat can automatically insert that canceled response into the context history for you.
We've mostly talked about synchronous calls. What if you want to kick off a background task that takes ages without blocking the chat?
Yeah, that's a current limitation of most LLM function calling APIs.
Yeah.
They expect that request-response pair together. So doing something truly asynchronous, where a function starts a job and maybe feeds results back later or continuously, tricky.
What's the workaround?
Usually you define a function like start background task and return it. The LLM calls that, gets an ID back immediately. Then you need a separate mechanism outside the LLM flow to somehow inject the results back into the conversation later. Maybe as a fake user message next turn. It's clunky. We're hoping for better native support for async or generator-style functions in future APIs.
What about the LLM calling multiple functions at once or chaining them?
Ooh, yeah. Parallel function calling, multiple calls in one LLM response, and composite function calling, LLM orchestrating a sequence of calls. Super exciting potential, more autonomous agents.
Wow.
But it dramatically increases the complexity and variability of the agent's behavior, needs really thorough evals. Often, it's best to disable parallel calling unless you specifically need it, just to keep things more predictable initially. Composite calling is amazing when it works, but still feels a bit jagged, inconsistent in current models.
Okay. Beyond text and basic function calls, LLMs are getting multimodal. Audio, images, video. How's that changing voice AI?
It's huge. Potentially transformative. We already talked about speech-to-speech models handling audio directly.
Right.
But now add vision. Top models like GPT-4o, Gemini 2.0, Claude Sonnet 3.5, they can all take images as input. And they're getting better than just describing them. They can count things, find objects, understand relationships in the image.
And video.
Gemini 2.0 Flash can process video, both the visual track and the audio track.
What kind of new voice apps does this enable?
One really interesting area is voice assistants that can see your screen. Imagine telling your computer, click that button or summarize this web page using voice, and it understands because it can see what you see.
Voice-driven web browsing or AI coding assistants that see your editor.
Exactly, that kind of thing. Feels like a much more natural way to interact with devices sometimes.
But does adding images and video mess with the latency for voice?
Yes, that's the big challenge. Audio, images, video, they use way more tokens than text.
How many more?
Rough numbers. A minute of speech as audio might be 2,000 tokens versus maybe a 150 as text. A single image could be 250 plus tokens easily. A minute of video, maybe 15,000 tokens or more.
Whoa. So keeping that real-time conversation going while processing lots of visual data.
Exactly. It's tough. Keeping the context size manageable is a major engineering hurdle. Think about asking your assistant about something from an image you looked at an hour ago, sending that whole image history back every turn. Probably too slow and expensive right now.
So how do people deal with that token explosion?
Strategies are emerging. Summarizing video down to text descriptions helps a lot. Using embeddings and RG techniques, only fetch the relevant visual snippet when needed. Don't keep the whole thing in context. And context caching, storing stuff for quick recall.
Are caching APIs good enough for this yet?
Current ones aren't perfectly suited for real-time, multimodal voice use cases, honestly, but we expect big improvements there in 2025 as these apps become more common.
We've mostly talked about using one main LLM, but you often hear about systems using multiple AI models together. Why do that?
You're right, that's very common now. Production voice AI rarely uses just one monolithic model. Even those beta speech-to-speech APIs often have separate little models for VAD, noise reduction, working alongside the main one.
It's like composing a system from specialized parts.
Exactly. Composability is a key trend. It lets you use the strengths of different models for different subtasks, can lead to systems that are faster, cheaper, more reliable.
Why not just use the single best, biggest model for everything?
Because even the best models have what people call a jagged frontier of capabilities. Amazing at some things, surprisingly weak at others. For really specific tasks or conversation states, fine-tuning a small, focused model can be better.
Like in that parts ordering example, a different model for different product types.
Yeah, a fine-tuned model can learn specific knowledge, like part numbers, or specific response patterns, how to answer common questions about that part. They can be faster, cheaper, and perform as well or better on that narrow task.
But fine-tuning sounds like a lot of work. Data collection, training.
It is. And crucially, you should always start with prompt engineering first. Often, you can get pretty far just by crafting clever prompts. It's much faster to iterate on prompts than to retrain models.
So prompts are like mini models you can test quickly.
Kind of. For embedding knowledge, try search and injecting results into the prompt first. For response patterns, give examples in the prompt. Only jump to fine-tuning if prompting really hits a wall.
Okay, use the right tool. What about tasks that just take too long for the main conversation loop, like complex reasoning or generating an image?
Right, that's where asynchronous inference comes in. You kick off the long task in the background, tell the user, okay, working on that, and let the main conversation continue.
Could you use a different, maybe slower but more specialized LLM for that background task?
Absolutely. Maybe a powerful reasoning model that's too slow for real-time chat, but great for analyzing something complex asynchronously.
How do you get the result back into the chat?
Again, it's often that workaround. One function starts the task and returns immediately. A separate process, when the task finishes, somehow injects the result back into the context, maybe disguised as a user message next turn. Still hoping for better native async support in APIs.
Safety is obviously huge. Guardrails. How do you stop bad outputs, hallucinations, prompt injection?
Yeah, content guardrails are essential. Code, or sometimes separate small AI models, designed to catch problems. Prompt injection, hallucination, outdated info, unsafe content.
Using separate models for guardrails is better.
Can be. Smaller models might be enough for detection. Different models might catch different weaknesses, defense, and depth. There are open source frameworks like Meta's Llama Guard, NVIDIA's NeMo guardrails that offer components for this. They were built more for text chat, but the ideas are useful.
Are these issues still as bad as they used to be?
Honestly, the latest big models are much better intrinsically. General hallucination is less common. Two main exceptions still pop up. Models pretending to call functions they didn't, fixable with good prompts and evils focused on multi-turn, and hallucinating instead of doing a web search when asked, helpful to just tell the user, okay, searching now.
And harmful content. Prompt injection.
The safety filters from the big labs are very good now at blocking harmful output. Prompt injection mitigation is also way better, though the attack surface grows with new modalities like text hidden in images. Generally, accidental injection from normal user chat is unlikely now. Deliberate attacks to subvert instructions, still possible. Always sanitize LM output before feeding it to backend functions.
It sounds like LMs are becoming general tools, not just chat engines.
Totally. Think beyond the main conversation loop. Use an LLM instead of complex regex for data extraction. Use it to post-process its own output format for UI, cleanup for TTS. We're even seeing recursion LLM calling itself to process a list. Summarizing conversations is another big one.
Like the LLM using itself as a tool.
Exactly. Expect more patterns like this in 2025, frameworks supporting it, maybe models trained specifically for recursive inference.
What about the system improving itself, learning during a conversation?
Fascinating area. Beyond big labs improving models with aggregate data, can an individual agent learn and adapt in real time?
How?
Think about feedback loops. Agent interrupts the user too much. Maybe dynamically increase the VAD, pause timeout. User keeps interrupting the agent. Maybe tell the LLM to give shorter answers. User seems confused. Simplify language. They offer translation. You can even do in-context learning. User corrects the agent on what MNI means. The agent uses that correction going forward in that chat. Creating these micro feedback loops is a key direction.
Okay, shifting gears slightly. We've seen voice AI move from just chit-chat to doing real jobs, following scripts, workflows.
Right. That's the shift from open-ended chat to deploying agents for complex tasks with specific goals, ordered steps. That healthcare patient intake example. Verify identity, ask about meds, ask follow-ups based on answers, all in sequence.
Trying to do that just with one giant prompt seems hard.
It is. Prompts get too long, instruction following degrades as context grows. You hit limits.
So what's the solution?
The state machine approach is becoming really popular. Define a series of distinct states in the workflow. Each state has its own focus system prompt, its own list of allowed tools functions, the relevant context, and define transitions to the next state.
And you can change things at each transition.
Exactly. Update the instructions, change the tools, summarize or prune the context, maybe using an LLM call just for that. Shorter, focused instructions in each state. Much more reliable instruction following from the LLM.
Balancing the script with allowing some natural chat seems key.
That's the art. Guide the LLM through the required steps reliably, but still allow natural conversation where it makes sense and doesn't break the core task. Tools like pipecap flows help build these state machines, often visually. Other ideas are emerging too, like multi-agent systems or parallel pipelines coordinating. Tooling is evolving fast.
With all this complexity, testing must be critical. Evils. How do you evaluate a voice AI agent effectively?
Right, evils are crucial. But voice AI evils are different from normal software unit tests.
How so?
Unit tests are usually deterministic. Input X gives output Y. Voice AI. Output is non-deterministic. Input is messy, multi-turn conversation. Results often aren't just pass-fail. You're looking at trade-offs, probabilities. Did it achieve the goal? How often? How naturally?
You need many runs, statistical analysis.
Exactly. Probabilistic evils. Run the scenario many times, see how often things happen, and simulating realistic user behavior is key because the user interaction is part of the system you're testing.
What kinds of failures do evils typically look for in voice AI?
Latency is always big. Time to first speech, time to complete response. Transcription errors, especially on specific data like addresses or names. Understanding and correctly verbalizing that data. And interruption handling, does it break gracefully? Does it recover context?
How do you start building an evil strategy?
Can start simple. Spreadsheet with test prompts, expected outcomes. Run them, maybe use another LLM as a judge to score the responses against criteria.
But for bigger projects.
You need more automation. Specialized evil platforms are emerging, like Coval. They're built for voice AI, often simulation-based. They help with iterating on prompts, offer standard metrics, audio quality, workflow success, function call accuracy, semantic similarity, help find problem areas, run regression tests, track performance over time. Investing in good evils becomes critical at scale.
A huge application area you mentioned is telephony, integrating with phone calls. Why is that growing so fast?
Yeah, a massive chunk of the fastest growing use cases involve phone calls. Companies using AI agents to answer calls, make calls, especially in call centers.
Why call centers specifically?
The big driver is often improving deflection rates, handling calls with AI instead of humans. The ROI can be really clear. If the LLM agent costs less per minute than a human agent and performs well enough, it's compelling. Leveraging that existing massive phone network means instant scale and real-world impact.
But it's not just cost, right?
Definitely not. Scalability is huge. AI agents handle volume spikes without making customers wait longer. That boosts satisfaction. Plus, LLMs plus APIs can often access complex legacy backends more easily than human agents struggling with old interfaces. The consensus is generative AI will totally reshape call centers very soon.
And beyond big call centers.
We're seeing more AI telephony for small businesses too, answering calls, giving info, basic scheduling. People joke about a future of AIs just calling other AIs. Might be some truth to it.
For devs building this, any key telephony jargon?
Good question. PSTN Public Switch Telephone Network, the regular phone network, needs something like Twilio to connect to it. SIP Session Initiation Protocol, used for IP telephony, connecting to call center tech stacks. Can use providers or run your own SIP servers. DTMF tones those touch tone sounds for navigating menus. Agents need to send those, usually via LLM prompting and function calls. Call transfers, simple ones, just connect elsewhere. Warm transfers involve the AI talking to the human agent first before connecting the caller. AI can do warm transfers now, too.
Agents often need outside info, array, and memory. How does that work in voice?
Right. Accessing user info, history, knowledge bases, web search, real-time data, it all falls under Retrieval Augmented Generation, RA.
Simplest form.
Look up user info before the call starts. Inject it into the system prompt. User is John Doe, calling about order 123.
But it gets more complex.
Oh, yeah. RA is a whole deep field itself, embeddings, vector databases, but often an 80-20 approach works. Use existing APIs for your knowledge base, write simple evals, deploy, monitor, iterate.
Does RA add much latency in voice?
It can, yeah. More than text or ag. You have the function call latency to trigger the lookup, plus the lookup time itself. So again, good practice to play a quick let me check message before doing a potentially slow RA query.
What about memory across calls? Remembering past interactions.
Super useful for personalization. Two main ways. One, save full conversation histories. Load the last full one, summaries of recent ones, maybe a function to dynamically load older ones if needed. Two, save each message individually with metadata. Better for complex histories, maybe multimodal apps with lots of images where saving full history is too much context.
Okay, last big topic. Deploying and scaling these things. How is it different from scaling a normal web app?
It's quite different. The core agent process isn't like a typical stateless web request. It's long-running, needs real-time audio streaming, uses WebSockets or WebRTC. That makes serverless platforms like Lambda or Cloud Run generally a bad fit for the main agent logic.
So what's the best practice?
Generally, containerize your agent early on using Docker or similar. Deploy those containers to compute VMs, start fixed, then add platform autoscaling, service discovery, failover.
Kubernetes.
Yeah, K8s is the standard for container orchestration at scale. Steep learning curve, but powerful and widely supported.
How do you update without dropping calls?
Long drain times. Let existing sessions finish gracefully before shutting down old instances. Cold starts are also a pain, need fast connections. Often easiest to keep a small pool of idle agents warm. Fast container starts are usually possible if you're not loading huge models locally.
Any common scaling gotchas?
VM sizing and container packing often cause early headaches. Start maybe one agent per CPU core, double the RAM you saw in dev. Make sure your orchestrator, like K8s, schedules new agents onto idle CPUs, not always the default. The key thing is the persistent low latency nature demands different infrastructure than typical stateless web apps.
This has been incredibly thorough. Looking ahead, wrapping up, what are the biggest things you expect to see in voice AI through the rest of 2025?
Well, growth isn't slowing down, that's for sure. More voice AI engineering happening.
Tech-wise.
More latency optimization, everyone chasing faster time to first token. Fuller integration of multimodality audio, vision into core models and APIs. Better testing and eval tools, specifically for audio nuances. Context caching APIs that actually work well for real-time multimodal use cases.
New platforms. Models. Expect new voice agent platforms from more players, and definitely more and better speech-to-speech APIs becoming available. There was a panel back in January with experts predicting things like universal memory for assistance, AI impacting Hollywood, AI moving from imitation to real understanding, even a contrarian take on robotics. It's going to be a fun year. Okay, so to quickly recap everything we've dived into, we hit latency as a critical differentiator. The leading LLMs like GPT-4o and Gemini Flash, the nuances of STT and TTS, including DeepGram, and startups like Cartesian 11 Labs, the whole audio processing pipeline from mics to Opus network transport focusing on WebRTC and edge routing, the surprising complexity of turn detection and interruption handling, managing context and the power of function calls, the rise of multimodality, using multiple AI models together effectively, including fine-tuning and async tasks, the importance of guardrails, the shift towards scripting and state machines for reliability, how voice AI evils differ, the massive integration with telephony, the role of RAG and memory, and finally, the unique challenges of hosting and scaling these real-time systems. And of course, what's likely coming next in 2025.
Yeah, that pretty much covers the landscape as it stands.
Hopefully that gives everyone listening that rapid but comprehensive understanding we aimed for. It's clear this field is moving incredibly fast.
Absolutely. The potential impact across so many areas is just huge.
And maybe a final thought to leave everyone with. As we rely more and more on AI for communication, for information, how might that shift things for us? How we interact as humans, maybe even societal norms. Something to chew on as you keep watching this space.
Definitely food for thought.
We really encourage you to explore further, maybe try building something yourself, and share what you learn. It's an exciting time. Thanks for joining us on the Deep Dive.